Right now, here we have our conical pendulum, and we want to find the magnitude and direction of the acceleration at that moment. And then we want to find the speed of the mass, and we want to calculate the tension in the string. So I'll start with the free body diagram. And in the free body diagram, I can see that that mass there has weight. The only other force I can see is tension. Now, there is an acceleration. The acceleration is going to be towards the center of the circular path. So I'll draw it here, but it's not really part of the free body diagram. This is a radial acceleration. It goes around in a horizontal circle. There shouldn't be any speed change, so I should only have radial acceleration. All right, looking at that, I can see that the tension is the force that I have to resolve into components. And there's a y component and an x component. And the x component is what contributes to the radial acceleration, and the y component of the tension cancels with the weight. So if I look back on my picture, I can see here's the tension. Here's Ty, and Tx is over here. And from vertical angles, I can see the angle theta is right there. So angle theta is with the y. So what that means is when I go back and draw my triangle for tension, it looks more like this. Tx here, Ty there, and T with angle theta. So Tx is T sine theta, and Ty is T cosine theta. So choosing my positive direction in the direction of acceleration, and the positive y perpendicular to that, I can see with F equals ma, I get the following equations. So for the first part, the total force in the x direction is T sine theta, and that equals ma, a being the radial acceleration. In the second part, I have the total force in the y direction is T cosine theta minus mg equals 0. So for part A, calculating for the acceleration, I can see I want to eliminate tension. So you can solve for tension in one of those and plug it in, or you can take equation 1 here and divide into it equation 2. So what I'll do is I'll take equation 2 and solve for T cosine theta. So T cosine theta equals mg. And I'll take equation 1 divided by equation 2 like this, and t's cancel, and I have sine over cosine, which is tangent. So tangent theta equals mar over mg, which is a radial over g. So the radial acceleration here is g tangent theta, which when I plug it in is 3.18 meters per second squared. Then I would say a radial is left towards the center of the path at that moment drawn. Okay, part B is to calculate the speed of the mass. Well, a radial is v squared over r, and I'm given r here. R is from the center of the path to the mass. R is given. R is not given, actually. R is that distance there, so I have to find r. L is given. L is the length of the rope there, and I can make a triangle, and I can see if L is here, R is there. There's angle theta. So sine of theta is R over L, so R equals L sine theta. So my radial acceleration is v squared over r, which is v squared over L sine theta. So the speed v is the square root of the radial acceleration, which I just found, times L sine theta, just like that. and I plug it in to get 1.66 meters per second. Now part C, calculate the tension in the string. Well, from my Y equation, I can see tension is mg over cosine theta. So I just plug that in to get 25.8 newtons.